Okay folks, this is Fukushima again. I'm doing the iodine 131 again with a slight modification to the equation. As you can tell, I've changed the Z to the Z minus, P times Z minus 1 over Z to another equation. It's P times X minus X over Z, X equals Z minus 1. I happened to load down a graphing calculator, and it suggested that equation would be better. It automatically converted it, actually. So I decided to go ahead and put it on here because it's a lot shorter. I've also changed your half-life here. New rule to the half-life. Units must be the same. If your Z, your half-life is in, say, days, like iodine is, but the units that are coming out of are being measured in hours, then you have to convert the units, the larger unit, the day one, to hours, and that's where I get this 192 right here in the equation, replacing for Z. Now the 15 is 500 sieverts that are being put out times 3%, which brings it down to 15 sieverts of iodine 131 are actually being released by reactor number 2 at Fukushima. And I got that from this guy right here. MBYE News, Fukushima radiation wind causes poisoning countries globally. Wikipedia, he was showing a thing on Wikipedia where it showed 3% of nuke byproducts are iodine 131, which is what I'm doing here. These are YouTube channels, by the way, that I got this from. Seeker was his YouTube channel name. The internet is overacting about Fukushima radiation. Here's why. February 12th to 17th. And this is the information I got off of him, which confirms the information I got off of the next one I'm listing. 73 sieverts in 2011 in reactor number 2 per hour. By 2017, that was up to 530 sieverts per hour. I consider that an increase. Now, RT America, radiation at Fukushima at highest levels since meltdown, February 6, 2017, slightly before the other guy, Seeker, confirmed the 500 figure. Doesn't have anything about the 70 figure. Okay. As you can tell, it's a much smaller numbers because I'm not running those huge numbers I was running the other day. And it's a lot easier with this new equation. I did add another equation here. Since you don't have the Y for this one, it's going to be 0. But once you do a complete run through for one half-life, you substitute D for Y, because each time you start a fresh half-life, D will be the initial amount. As you can tell, D was 1455, D1 was 2547, and you can tell it continues to go upwards, but it's slowing down. Forgot to put my days on here. Okay. I guess it really doesn't matter whether I put days on here or not, but I'm going to put them on here. Figure 16, 24, 32, 40, 48, 56, 64, 72, 80, 88. Okay. There's the days. For anybody who wants to know, that's how many days it takes for this equation to go. As you can tell, by the time you get down to 88 days from whenever this reading was taken in 2017, it should have boosted from the original number of 1455 all the way up to 5574. But as you can tell, it's declining as to how fast it's increasing. So it's not increasing as fast as it was. Well, that's basically it. I really did this one just to redo it with this new equation here, which is a lot simpler. Adding that x minus x over z times p instead of that big long one I was using, it makes it a whole lot easier to do. Now, just remember, this is Fukushima reactor number 2, and these should be actual numbers based on known information available on the internet. Like I say, I got the 3% from this guy right here, and he got it from Wikipedia on the internet. And I used that to figure how much radiation and how it will grow. And as you can tell, it's going to grow. I can even sit here and do a quick calculation for you to show you how much it's going to grow. You figure, all you have to do to figure out how much it's going to grow is to take your 192 from here and divide it into your remaining element, which is 5574. Okay, that will come out, that's 2, 4, 18, 2, 3, 3, 3 and 5 is 8, 2, so that's 3. Six, 21, 5, 6 from 4 is 8, 2 from 5 is 3, wasn't 6 from 4, that's 6 from 7, 1, 3, 0, 4. So the equivalent amount of units will go up to 32. That means it's still adding. That's doubling. Even today, as long as it's been since the accident occurred, the continuous output puts it to where it would double in continuous output effectively. What that means is it's putting out more than you might think. So that's pretty much it that I wanted to show you. You can look at the figures yourself if you want to. They'll be right here. Right there's the thing. There's most of the figures right there. Then of course you got this figure over here I just did, which says that the number of sieverts might actually still go up to 32 for this. And if that figure's incorrectly, then the sieverts should go up to 1,000 sieverts within, should go up possibly upwards of 1,000 sieverts by now. But some of them have longer half-lives, so their sieverts wouldn't go up as fast. But you have to consider, see this 8,300 figure? That's the amount that you had on hand at the beginning of that cycle, that half-life, plus what you've added. Then 2,798 is the amount that decayed, and 5,574 is the amount that was left over, which came to an equivalent of 32 continuous output by the end, which worries me. Okay, well that's what I wanted to show you. Have a good one. Hello.